All right, so you ready to go over this question in the whiteboard?
Yes. Let's do it.
Okay. So what you're going to have here, oops. Okay, so let's say, all right, so this is just a neuron over here.
Mm-hmm.
And when you have, so do you know what myelin is?
Yeah, that's like the structure that covers the
Mm-hmm.
dendrite.
Yeah. So I just drew like this kind of like, basic kind of neuron. It's supposed to be like the long part of the neuron.
Yeah.
And what happens with myelination is that you have, it's going to be surrounding the the length of the neuron,
Yes.
and it's going to be like fat. So it's not going to conduct electricity. And you'll have them like this. Like you'll have the different myelin sheaths. Kind of. It's not going to be like one entire continuous thing that's around the entire.
Yeah, they're like little section now things.
Exactly. So okay, I'm gonna go back to drawing the non-myelinated ones. So if there's an action potential here, right? It's going to have to travel the entire length of this neuron. Okay?
Mm-hmm.
But if we have an action potential here on the myelinated neuron, it's going to go by, so here I'll draw, so the regions between the myelin are called nodes of Ranvier,
Okay.
and for the action potential to travel through it, it's going to go to that node, and then to that node, and then to that node. Right?
Okay.
And that's what the saltatory conduction is. It's essentially a word that means jumping. So
Okay. So
it's
this
yep.
basically means that the synapses jump between the nodes of Ranvier.
Yeah. So the action potential will, instead of traveling through the length of the neuron, and let's say through the length of one neuron, through the length of another neuron, etc. That's going to be how the action potential propagates for regular neurons. But if you have myelinated neurons, the action potential will jump from each node of Ranvier to each additional node of Ranvier, and this results in a much faster conduction. So that's
Okay.
why, yeah. So that's why myelination is a big part of you know the nervous system, because it enables action potentials to travel significantly faster.
Got it.
Right?
Okay.
Yeah. And then what these other definitions are, like the axon hillock and the synaptic bulbs and things like that.
No. What is the axon hillock?
So, so if I have some type of neuron here, like that,
Mm-hmm.
so you have the dendrites are going to be like here.
Mm-hmm.
Maybe I'll use a different color, but the dendrites are going to be like the branches here, like
Okay.
that, and that. And this is the body of the neuron, and that's referred to as the soma.
Mm-hmm.
And then we have the long, axon. And the ends of the axon will have dendrites as well, like essentially, kind of like these tendrils or like little hands or something like that, like limbs almost, and they just enable the action potential to travel from one end or one axon hillock to the next one. Like the next one would be like here, like that.
Right. So the ends of the axon and the tips of the soma will all have dendrites?
Oh, yeah.
Okay. Okay. So then the hillock is what again?
So the entire thing, I'm just gonna paste that here. So this is the what a neuron looks like. So I pasted it. You could see it, right?
Yes.
Yeah. So you see how the dendrites are these branches essentially that are along the cell body of the neuron, and the cell body, can also be called the soma.
Uh-huh.
And then the axon hillock is simply the part where that long end starts to become long. So it's like the interface between the body of the cell of the neuron and that, the long portion. And we see that the end of the neuron, at the end of that long portion, we have the axon terminal, and that's where you'll see, well, if you simply have another one, right, like this, like that, what you will see is you'll see neurotransmitters being released here. Oh, what?
Huh?
Yeah, I don't know. The thing that I drew disappeared, but here, I'm putting it in again. So you're going to have these neurotransmitters released at the axon terminal, and they get picked up by the dendrites of the next neuron, and they'll travel through, and at the end of the axon terminal of the next of this neuron, it'll send that that signal down to the next neuron, and that's what this gap here is the synaptic cleft.
Oh, so neurotransmitters basically travel across the synaptic cleft in order to keep messages rolling to every neuron for a synapse.
Yeah.
Okay, so hold on. To another across the synaptic cleft. This allows communication from neuron to neuron for synapse. Okay, got it.
Yes. So yeah. The diagrams that I just pasted here, are, well, they have myelin sheaths, but yeah, generally speaking, if they don't have the myelin sheath, the action potential will have to travel that entire length. Yeah. But if you do have the myelin sheath, it's gonna jump from here to that node, to that node, to that node, and
that much more of a difference in terms of getting a synapse across much faster.
Exactly. So,
and that's why you don't want to have demyelination, which is what happens a lot with multiple sclerosis patients, right?
Yeah, and a lot of Alzheimer's, dementia, lots of things like that.
Yeah.
In the brain, so that's what white matter is. White matter is
yes,
is mostly the myelinated axons.
Yes.
So and you see how they said in Latin saltus means to jump.
Yeah.
So that could be something that can help you remember what saltatory conduction is.
Latin, saltus, Alright, perfect. So that's good.
Yeah, I'll put in another kind of diagram to kind of show this. So you could see the non-myelinated axon, it's just running along the length right there.
Yes.
But in the myelinated axon, it jumps, and that makes it significantly faster.
All right, perfect. All right.
Okay, so the next question you have, you can just paste it into the Google Doc, and then
Yes.
I'll talk about that.
Copy. There you go. You see it?
One sec. Not yet. Oh no, I see it now. Okay. Okay. All right. So this is talking about the regulation of fatty acid synthesis.
Yes.
And that's going to be, one of the metabolic pathways. And so we want to know, I guess it's asking which is true, so we're going to have to kind of go through each. But let's see. So A says acetyl-CoA carboxylase is not the rate-limiting enzyme. Okay? And then B says acetyl-CoA carboxylase is stimulated by epinephrine. So that's saying if epinephrine's, if your fight or flight response, for instance, is activated, that it should start to, it'll stimulate this acetyl-CoA carboxylase enzyme. Okay. And then, so all of it seems to be about the enzyme acetyl-CoA carboxylase. Now, what is a carboxylase?
Would that be an enzyme that synthesizes carboxylic acids?
Well, let's think about just the carboxylase.
Okay. Enzymes that convert like carbohydrates into oxygen?
So a carboxylase is going to be something that takes in CO2 from like the environment, let's say, and adds it to the molecule. And
so it takes CO2 from the environment?
Yeah. It from the environment might be variable, but think of it as CO2 being added, yeah.
And is added to molecules?
Yeah. So, for instance,
Okay.
So for instance, you can have what I just drew over here. This is what
Okay.
acetyl CoA looks like.
Oh, there's a sulfur there.
Yeah, because the CoA so like the CoA bound to the thiol, that is
Yeah.
the CoA, like coenzyme A or whatever, like on its own.
Yeah.
But you can see that it can add itself to things, and it'll have to get rid of that hydrogen. But this is what acetyl CoA looks like, and it's a good molecule to know what know the structure of, because it comes up a lot. Like basically all of the biological macromolecules, like proteins, carbohydrates, fats, they all at some stage of their metabolism turn into acetyl CoA. So that's why acetyl CoA is a very good. It's a molecule that's going to come up a lot. And now a carboxylase, right? So okay, let's say that a carboxylase is working, or is being, let's suppose a carboxylase is going to act on that acetyl CoA. That means that CO2 is going to enter as a reactant here.
Okay.
And in the Krebs cycle, you'll see a lot of examples of decarboxylases. And
Okay.
decarboxylases will do the opposite. It will remove a CO2.
Got it.
So, yeah. So, okay, now let's think about what happens here when we take the acetyl CoA here and we have a carboxylase act on it. What do you think would happen? Like, basically, we need to add the CO2 to the acetyl CoA.
Okay. So, what is it exactly you're asking?
Oh, so what happens if we... So this over here
Uh-huh.
is the...
Yeah, the acetyl CoA.
And if we're adding CO2 to it,
Mm-hmm.
what should we see?
Shouldn't we see them come apart?
When you say come apart, what do you mean?
Like, oxidize?
What do you mean when you say oxidize?
Well, we're adding CO2, or we're reducing? Sorry. Sorry.
So if we were doing any redox, right, the enzyme in question would be called like a dehydrogenase or something like that, right?
Oh, okay, dehydrogenase. Okay.
But since we're only talking about a carboxylase, and we know a carboxylase really just does one thing, it adds
Just
carbon
takes
dioxide.
CO2 and it adds it. Okay.
So let's see if we added the if we added the if we added the CO2, what molecule would we get?
If we add CO2 to the whole acetyl CoA thing,
So
I'm stumped. I don't know.
it's okay. So how about this?
I was thinking about adding something to the other side.
Mm-hmm.
But we're gonna get an aldehyde?
Kind of closer to what I think you said before, a carboxylic acid.
Oh, okay.
But you see how what we added here, right, is CO2. You have that one carbon here, and then the oxygen up there, and then another oxygen here.
Yeah.
By the way, can you see like my like cursor here?
Yeah.
Like you see, okay, so where's my cursor? Oops, where's my cursor now?
Like over the picture.
Yeah, where it says 57%.
Mm-hmm.
Okay, cool. So yeah, that's what happens when you have when you carboxylate something, because you're adding CO2, and CO2, by the way, looks like this, right?
Yeah.
CO2 is a linear compound, right?
Mm-hmm.
Because of those double bonds to oxygen.
Yes.
So we want to, we want to take that into consideration, because essentially what we're doing is we're breaking one of those double bonds to oxygen,
Mm-hmm.
right? And you're going to create, or rather, the molecule is going to bind to the carbon here, right? And carbon can only bind to 4 things. That means one of the bonds to oxygen, this one here, is gone, right? So that's why this can turn into, you'll still have this C double bonded, God. So you'll still have the C double bonded to the oxygen, like this over here, right?
Mm-hmm.
But this one here would be single bonded to the oxygen, right?
Yes.
Because this is where, the molecule or whatever binds to, like the reactant.
Mm-hmm.
So that means this is going to be, an O minus, and then this is going to be the molecule. Whatever molecule we're adding it to.
Yeah.
And of course here there's resonance, right? So this can go there, this can go there.
Mm-hmm.
But you can see how this over here, it's essentially adding a carboxylate group. Like all you need is the hydrogen, like a hydrogen here, to turn it into a carboxylic acid, right?
Mm-hmm.
But yeah, that's what you're gonna end up with over here.
Yeah.
And what this does is, so the name of this molecule is malonyl CoA, but
Mm-hmm.
yeah, let's think about which of these things could work, right? Because okay, if they're saying that, so they're asking what's true in the regulation of fatty acid synthesis. So if you're making fatty acids, right, you're essentially, trying to produce a high energy type of molecule.
Yeah.
And so okay, so for some of these choices, like B, that says that it's stimulated by epinephrine, right?
Yeah.
So if that happened, right, what you should be seeing is, so if that was to happen, that means that when you have epinephrine in your body, you're going to take the acetyl-CoA and turn it into, like, the malonyl-CoA. But
Mm-hmm.
we want to see, like, what the overall, what this reaction really does in terms of synthesis of fatty acids, because that's going to happen when you need to store the energy of the fatty acid,
Okay.
right? So it should be suppressed by the epinephrine,
Mm-hmm.
right? And then, and also, like, right away you can kind of tell that choice C and choice D are opposites.
Yeah.
And when they're opposites like this, that means they both can't be correct, right?
Yeah.
And that's called mutually exclusive. So that could be like a shortcut here. You can kind of see that, this and this are saying what they're saying, but C and D are saying the opposite thing, because so C is saying that this enzyme is inhibited by insulin,
Yeah.
and then D is saying that this enzyme is inhibited by glucagon, and we know that insulin works in the opposite way from glucagon, right?
Yes.
So insulin's going to, involve taking the blood sugar, into your tissues, like from the blood, right?
Hmm.
And then glucagon will be taking the glucose and the sugars from your tissues and then putting it into the blood, right?
Oh, okay.
So like if your blood sugar is too high, right? Like for someone who's diabetic, let's say, they would take their insulin shot, right? Because the insulin will if there's too much blood glucose, it'll take it from the blood and it'll put it into some organ
Hmm.
or some tissue. And then glucagon will be the opposite. So right away, you can, if you see that two choices are mutually exclusive, that can help you understand that only one of those two choices must be the answer,
Got it.
right?
Okay.
So yeah. So now, if we're thinking about the fatty acid synthesis, we want to see, is this going to be something that happens when you have too much sugar in your blood, or is it going to be something that happens when you have too little in the blood, right?
Yes.
So, and it says inhibited, right? So okay, let's say that C is true. If C is true, that means that when you have too when the when your blood glucose is too high, it will stop this step of the fatty acid synthesis. And let's think about if that's true, because insulin's released when our blood sugar is too high. So this fatty acid synthesis step here, we want to ask ourselves, is that going to go up when we have high blood glucose, or is it going to go down when we have high blood glucose? Yeah.
I would say that it's gonna go. Uh, it would go down. No.
You're saying,
Wait. Repeat the question.
oh, sorry. So if your blood glucose is high, right?
Yes.
Would your body want to, let's say, produce fatty acids?
No.
Good. So, okay, that's the one that says that the carboxylase is inhibited by
Hmm.
insulin. But then D says that it's inhibited by glucagon. And again, we want to ask ourselves, is this going to happen when there's high blood glucose or low blood glucose, right? So
It would
glucagon
be
gets
when there's
what's up?
high blood glucose.
Yeah, so that if that reaction proceeds when there's high blood glucose, when there's
Yeah.
low blood glucose, it should be inhibited, right?
Yeah.
Because the glucagon is going to be something that's released when you have, low blood sugar, and you're going to just basically create or raise the amount of blood sugar. That's what the glucagon is responsible for. And if you're increasing the amount of blood sugar, you're not going to be producing fatty acids.
Got it.
Since
Okay.
fatty acids, like, there's fats, there's proteins, there's, uh, you know, complex carbohydrates, but
Hmm.
um, the most important thing is glucose, right? And we talked about how other things, proteins, fats, they can turn into glucose, um, but yeah, we want to first of all make sure that the amount of glucose in our blood is where we want it to be, and then from there we can kind of make decisions about, are we going to be producing more fats? Are we going to be producing more proteins, things like that.
Yeah.
Okay.
Got it. Okay. Um, okay, I know that question. Know that. Cool. Okay. There's an action movement after repeated simulation. This is called. Okay. One second here. Okay. Boom, boom. All right. Beta oxidation takes place in the mitochondria. The following osteoclast activity is upregulated by the parathyroid hormone. Okay. Steroid hormones are synthesized from amino acids. That's known. So, okay. Hypothalamus and this stuff I don't understand. So let's put that. Okay. Do you see it? I put the new question.
Okay.
Okay. Oh.
What's up?
Know what you have over here.
Okay, so for this, it's Do you see what I'm showing you?
Okay, I see it.
Yeah. So this is so the okay. So the hypothalamus, right? It's going to so what it releases are releasing hormones, and here what we have. So it's kind of hard to see the hypothalamus part of this, but it's essentially just what's up here.
Okay.
But and then downwards, there's going to be the anterior pituitary, which is the one in the front, and then there's the posterior pituitary in the back. And
Mm-hmm.
now, the way that they get that they secrete into the pituitary is a little interesting. Um, so basically, stuff that goes from the hypothalamus to the posterior pituitary get get transferred through um, through the neurons,
Mm-hmm.
right? Um, but when things get transferred from the hypothalamus into the anterior pituitary, it does so through the blood vessels.
Okay.
Okay.
Got it. All right, so that makes sense.
Yeah. So for this question here, I'm just trying to see if I can find a more clear diagram. But what you're oh yeah, here, this one's better. Oh wait, it's a different language. Yeah. So okay, the question's asking the capillary link between the hypothalamus and the anterior pituitary is referred to as. So this is so generally speaking, we have so if we look at what's being transferred from the hypothalamus to the posterior pituitary, you have these neurotransmitters or hormones being transported through the axon, through the actual nerve,
Mm-hmm.
right? And we can call this neuroendocrine.
Yeah.
But what gets so that this OT release and ADH release, OT is oxytocin, ADH could also be called
Antidiuretic hormone.
yeah, it can also be called vasopressin. So that those are made in yes in the hypothalamus, and then they travel through the actual neurons, right?
Mm-hmm.
To and then they come out in the posterior pituitary. But if we look to the left, the one that's comparing it, showing you the anterior pituitary, you see that you still have the neurosecretory cells, which is the ones that creates the hormones in
Mm-hmm.
the hypothalamus. But then down here, I'm not sure if you can see my cursor.
Yes, I can.
It's around where?
The hypophyseal
Yeah.
portal.
So you see how over here there's no veins, right? There's no blood vessels here, right?
Yes.
Over here, but here you see that there is blood vessels, right?
Mm-hmm.
So that just means that that when the releasing hormones get released from the hypothalamus and when they enter into the anterior pituitary, they do so through blood vessels.
Yeah.
Yeah, through blood vessels. Whereas when hormones from the hypothalamus go to the the posterior pituitary, they are simply released from the neurons.
Yeah.
So that's the main difference here. Now, for the question, so yeah, vascular system is going to be, the bloodstream.
Yes.
Circulatory system is kind of like just another way of really saying
Yeah.
blood system or whatever. But since they're asking for something very, very specific here,
Yes.
we're not going to have A or B be our answer. And then C, releasing inhibiting system. I think that's just trying to tell you something about maybe negative feedback loops, but that's not going to be what it's called either. So it's going to be called the hypophyseal portal system.
Yes.
And yeah, that's what you have like over here.
All right, great.
Mm-hmm.
Let's see what's next. Means that a gas exchange in the lungs. Yeah, alveoli. That's easy. Space between the membranes. Yes. Just a quick question. How many... The left lung is what only contains one lobe, yes?
Or
does it have more than one?
When you say lobe, what do you mean exactly?
Well, no, because there's a question here that just says, like, one of the statements here, which it was wrong, but it says each lung has 2 lobes.
Oh, you could show me, you could copy and paste that.
Okay, yeah, because I got it right. It was asking, like, what's true about lungs, but...
Oh, okay.
Actually, you know what? It would be good to go over it anyways.
Sure.
Because then I'll know why the other stuff is not true. Okay, there you go.
Okay. Okay, I see. So, yeah, so something about the lungs that's kind of weird is that they're asymmetrical when it comes to the type of lobes that they have.
Yeah, because I know it would be less on the left because of the heart needs to make space for it.
Yep. Yeah. So there's essentially... Here, I can probably find a good picture. So, yeah, so it's essentially going to be like this here. So, they're both going to have... Well, okay, let's start with the left one. So the left one has 2 lobes. There's a superior lobe. There's an inferior lobe. And then the right lung, it also has a superior lobe. It also has an inferior lobe, but there's a new middle lobe, which is in between the superior lobe and the inferior lobe.
Mm-hmm.
So yeah, for this question, each lung has 2 lobes. Only true for the left lung. The costal surface of the lungs rests against the spine, so that's the part that's connected to the the rib cage essentially.
Yeah.
So that's not. So C would be right if it said that it rests against the ribs.
Okay.
And that the ribs will be in front of the lungs, but it's the spine would be behind the lungs, and it's not going to be related to that. And then D is incorrect. They're asymmetrical. So yeah. Oh yeah, and then the base of the lungs rests on the diaphragm. Yeah.
Okay, great.
Mm-hmm.
Yeah, chemostrenching irritant receptors, I know about that. Better come see. Okay, yeah, this was one I did not understand whatsoever. And it seems like it was one of the hardest questions because everyone pretty much had the same mixed results. There you go.
Oh, okay, yeah. So this can be a little annoying just because, I mean, for the most part, you can just understand. So okay, so there's Henry's law, there's Boyle's law, and there's also Charles's law. And the reason that I think this question's a bit annoying is because the ideal gas law incorporates all three. It incorporates Henry's law, it incorporates Boyle's law, it incorporates Charles's law. But this is just asking you specifically which one is associated with which. So we're going to have another kind of situation where, two choices will be mutually exclusive.
Yeah.
So here, let me talk about the different types. So we can have PV equals nRT.
Mm-hmm.
I mean, that's just that's in reality. What's up? Yeah. So that's what in reality makes it so that we don't have to really know specifically Henry's law and Boyle's law and Charles's law, but sometimes they could ask you that. So I'll show you how the different types of laws come in. So basically, we see which tell me in terms of proportionality relationship. What is the proportionality relationship between pressure and volume?
Isn't pressure proportional to like the amount of volume something may have? So if there's less volume, there's going to be more pressure. If there's more volume.
So let's say, this is all equal to a constant, right?
Yeah.
And let's say we increase the pressure.
Mm-hmm.
That
means there's less volume, no?
What's up?
When more pressure equal less volume.
Okay. So,
like if we think of it as a let's say in the physics portion of these exams and whatever, or just in the explanations in Anki, they have like the cylinder when they explain the different equations.
Mm-hmm.
So it's basically like, if you have less condensed but the same amount of gas, it's more concentrated and the pressure is increased, which gives more room for volatility if it's going to burst. But if you keep it big, then there's much more volume, less pressure involved, even with the same amount.
Yeah. So here, let's talk about N is the number of moles, but we're going to keep that, constant. R is, literally a constant. And then let's say T, we're not changing the temperature. So if you raise the pressure, the volume must what?
Go down.
Yeah. And if you decrease the pressure, the volume will
go up.
So what type of proportionality is that?
They're inversely proportional.
All right. And you can write that like this. So pressure, this is the proportionality symbol. And if it's an inverse, it'll be 1 over
V.
Volume, right? So, okay. So this here is going to be what was the guy? Boyle's law. Okay?
Yeah.
All right. Now let's think about, okay, what about, the other relationships? So how about, let's say, the relationship between, let's say, okay, that's that one. Let me just do something. Okay, let's say okay, how about, let's say the relationship between pressure and temperature, or, between volume and temperature. These are going to be direct proportions, right? Like if pressure goes up, the temperature goes up. If volume goes up, the temperature goes up.
Yes.
So the relationship then between these values and temperature is going to be Charles's law. All right.
So pressure, the more pressure there is, the less temperature.
Oh, so these are direct. So sorry, what did you say? You said less?
Because you have P is not equal to T, so that means pressure wouldn't be can't be like proportional to temperature.
Oh, so that's the proportionality relationship. So that means if pressure goes up, so does temperature.
Yeah.
And also, if volume goes up, so should temperature as well.
Yeah.
So, yeah. So the relationship.
Well, that makes sense. Like, I think the best explanation for that would be like a car tire, like the PSI on a car tire. If you go from summer to winter, you always need to refill the air into your tires because once the heat is gone, all the pressure in the tires goes down by at least 6 or 7 psi.
Yeah. Because if you think about it, when you add heat to something, let's say a gas, and the temperature goes up, the molecules are going to be moving around much faster. And if they're moving a lot faster, they're going to be hitting the walls of the container. In this case, the case you mentioned in the tire, and if it hits the container walls with more energy or kinetic energy, that means that the container is going to be experiencing a higher pressure.
Yeah.
And
Because
then
the kinetic energy is up.
Yeah, and also when you have an increase in temperature, and you have the increase in the average kinetic energy of the particles, if the container volume isn't rigid or whatever, the volume could increase as well.
Yeah.
Right. So okay, those are Charles's laws. Now Henry's law is a little oops. So Henry's law is what relates partial pressure of a gas. So like let's say let's say partial pressure of gas X is going to be equal to the mole fraction of gas X multiplied by the total pressure. Right? So, and the mole fraction here is essentially just a way for you to determine like what percent of the total gas, let's say, and let's say it's a mixture of gases, what percent of it like leads to. So let's say I have let's say that the partial or the mole fraction of a gas is, I don't know, 0.5. And then let's say that the total pressure of the gas is, let's say, 3 atm, right?
Mm-hmm.
So if you wanted to find then the partial pressure of the gas, you would take the mole fraction of the gas, which for this I wrote is 0.5, times the total pressure, which I wrote was 3 atm, and then you'd end up with 3. It'll be 0.5 times 3, and 0.5 is 1 over 2, so it could just be 3 over 2 or 1.5 atm. So yeah, Henry's law is what states that the partial pressure is dependent on the mole fraction of that particular gas. And this works when you have a mixture of gases.
So that partial pressure is dependent on the mole fraction of gas.
Yeah. So this would be Henry's, and then there's one more that I think it would be relevant, and it's just yeah. So I didn't use any real values here, but let's just say the mole fraction of gas X, times the total, plus let's say mole fraction of gas Y times the total, plus mole fraction, let's say, of gas Z times the total. Like, this would just give you the partial pressure of gas X. This will give you the partial pressure of gas Y. This will give you the partial pressure of gas Z. So if you just add these, you should be getting your total
pressure.
Yeah, and this is Dalton's.
Got it.
Yeah, so since this question's asking about how much, so let's say you're inhaling air, and they're asking how much of that air that you're inhaling gets dissolved in the blood.
Yes.
So yeah, that will be Henry's law, since that means that dependent on the partial pressure of the oxygen, that'll determine how much gets actually dissolved into the bloodstream.
Got it.
Yeah, and then Boyle's law, relationship between pressure and volume, being inversely proportional. C, ventilation perfusion coupling. That's essentially just a fancy way for them to say that the air that you're, inhaling, that's the ventilation part, and perfusion is the air or the oxygen that you're inhaling being absorbed into the bloodstream, right? So it's
a fancy way of saying what?
It's a fancy way of saying that. So let's see. I can write. So ventilation part is essentially the airflow, and then the perfusion part is, I guess, how much, let's say, O2 in the air gets dissolved into
the bloodstream.
The blood, yeah, and they're
okay, because it says here airflow matches blood flow, allowing the lungs to reroute blood to better ventilated areas.
Yeah. So that kind of shows you it's an automatic thing that luckily our bodies do for us, but but yeah, it kind of makes it so that because in order for us to get oxygen to our body, first of all we need to inhale it, right? And then second of all, in the in our lungs, the gases come I guess go through like the alveoli, and the gas gets exchanged from the alveoli to the blood vessels, like the pulmonary like artery. So
Yeah.
it's really just saying that the inhalation of the air and getting that air to be dissolved into the blood are coupled. So it's not like and they're going to be related. Instead of them, if they weren't coupled, then we might be getting in way too much airflow and not enough perfusion, or we
Yeah.
might be getting not enough airflow and too much perfusion. So it's just showing that the two, when they're like when anything's coupled, it just means that they're connected. Yeah, and then pulmonary gas exchange, that's going to be the thing that that's the thing that happens when they're coupled. You have the gas getting taken in by the alveoli, and all of that happens because of the partial pressure gradient.
Mm-hmm.
Like, yeah.
Okay. Atrium, yes, the pulmonary veins. Do you have a diagram on the blood flow of the heart?
Yeah, I can get that.
I remember having that memorized before, and just need a picture to reinforce that.
Mm-hmm. Do you need that just for the heart or connected to the pulmonary?
I guess both wouldn't hurt.
Okay.
The question I was just looking for is referring to like the only answer choices were the aorta, pulmonary veins, pulmonary arteries, and the vena cava. So that would be only the blood flow of the heart.
Okay.
Yeah. Okay. Yeah, we go in through the superior vena cava and the inferior, and then it goes through the bundle of His somewhere, no? Through the right ventricle, out through the lungs, and then from the lungs goes in through the pulmonary vein into the pulmonary artery out the aorta, and pulmonary vein into the left atrium,
Mm-hmm.
and then the left ventricle, and then through the pulmonary artery into the aorta.
Mm-hmm.
Look at that, I still remember things.
Yeah. Good job. Also, do you mind if we end at like pretty soon, like in 3 minutes? I mean, I'll just charge you for the 1.5 hours because we have
that's fine.
technical stuff. But yeah,
No
I just
worries.
have another thing at 8.
That works, that's no problem. Oh, this is like a textbook explanation. It's good. One of these photos you have here.
Yeah, yeah. I even have a different a different doc that goes into this with even more in depth that I can share with you.
Okay.
Mm-hmm.
Okay. So I'm pretty sure that's all I needed for clarity so far. Still going through the other stuff over here. Cool. All right. So, everything else going okay with you otherwise?
Yeah.
That's good. That's good.